Let me begin with a word of prayer. Excuse me. Heavenly Father, we thank you for this day. Again, I thank you for this class. Just ask you to guide our steps today. Help us to glorify you when we do. And just to understand the basic theory of the nth order problem, Lord. In your name I pray, Lord Jesus. Amen. All right, so let's get started. So today we're talking about the nth order problem. Linear ordinary differential equation. So first order business is defining what that means. All right, what do I mean by a first order? And so the starting point here, I should say I is an interval. What do we mean by that? What's an interval? So here we have in mind either it's an open interval or it's closed open or open closed or closed, or what's the other possibilities? You could do a to infinity, a included to infinity, minus infinity to a, and minus infinity to a included, and then what's the last one here? The whole thing, right? So these are the intervals that I have in mind for the following definition. And if you don't write all that down, it doesn't matter. Okay, so, and by the way, I'm in chapter 3 of my notes, which I'd like you to read. So chapter 3. So chapter 3 of my notes is basically chapters 4 and 6 in some sense of the text. And it's all put together in one thing. And that's what I'll be covering for the next next story arc of class. Let's see here. So definition. Let I be interval. And A0, A1, and so forth, all the way to A sub n and f be real valued functions. Real valued functions on I. All right. Such that, and this is important. Oh man. Oh, that's weird. That's annoying. I really don't like the numbering, but I'll stick with my notes. So here it is. Why did I do that? Anyway, a sub naught of x is not equal to 0 for all x in I. And then here's the deal. We say a sub 0 times the nth derivative with respect to x of y plus a sub 1 times the n minus 1th derivative of y with respect to xn with respect to x plus dot 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 a sub n minus 1. This enumeration is really weirding me out. It's been a few years since I wrote these notes, and I'm sure I was basing them on some book I had or something, but it's really bugging me. I'm going to let it go, though. So the thing, I'll just tell you what's in my mind. Sometimes I would enumerate these like, this is a sub n, n minus 1, a1, a0. So some other day I might number them that way. It's just a question of like labeling, you know. Anyway, this is a nth order linear differential equation. All right, that's what it is. The coefficient functions are the a0 through an, right? And this f over here is the so-called inhomogeneous term. And what's the deal with that? So basically, if f is identically equal to 0, then let's call this star is homogeneous. And if f, if f of x is equal to 0, not equal to 0 for at least 1x in I, then the star is non-homogeneous. So what is star? So this whole differential equation right here is what we're going to call star. And so the project of this class for the next about 3 weeks is to learn how to solve these and understand the solution to them in a lot of different ways. Today we're just talking about the theory of the problem. All right. All right, so that's the first order of business. The next order of business is to rewrite this in a way which is easier to think about. So we can introduce operator notation. All right. So what's operator notation? So big D is d dx. All right. And then what's d squared? It's d squared, dx squared, etc., right? So I can rewrite star using operator notation as follows. I can say, well, it's really just a sub 0 times d to the n. The numbering's really bothering me, guys. All right, I'm gonna leave it. All right, a sub 0 plus a sub 1, d to the n minus 1. All right, this acts on y, right? This acts on y. A n minus 1 d acting on y plus a sub n times y, right, equals to f. Okay, so we've rewritten star as an operator equation, but we can do a little bit better. See, we can pull the y out here and instead think of a sub 0 d to the n plus a sub 1 d to the n minus 1 dot 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 plus a sub n minus 1 d plus a sub n. All of that is a differential operator. It acts on y, and it gives us f. So really, we can understand star instead as an operator equation. See this right here, we can just give it a name, call it L, right? For linear transformation. See, it's a linear transformation because if you, excuse me, I'll get back to that, but so this is equivalent to saying L of y equals to f. So this right here, in brief, this is, you know, a concise notation for the differential equation star. Now we'll get into a lot more details about the operator stuff another day, but I'm just going to tell you this much. So for today, if you take the jth derivative operator and you act on, say, cy1 plus y2, you can prove that you can pull out the constant and take the jth derivative of the first function and then add the jth derivative of the second function like that. So this means that the jth derivative operator is what's called linear transformation. Now, I say transformation, but perhaps I should cross that out and say operator. That'd probably be a better thing to say here. What's an operator? See, an operator is a function of functions, really. It takes in a function and it outputs a function. So like here, the input into the jth derivative operator is whatever function you're differentiating, and the output is the jth derivative. So like what I'm talking about here is like we're mapping y to this thing, which is just another notation for the jth derivative of y, okay? Here I'm assuming that x is the independent variable. All right. So that's the first thing. Now, claim L is a linear operator. All right, because the formula for L is built from a sum of linear operators, we can prove that in fact L is a linear operator. And why is that? Why is that interesting? So that's interesting because that means that L of y1 plus y2 is equal to L of y1 plus L of y2, right? And L of a constant times y is a constant times L of y. I mean, that's what I mean when I say that L is a linear operator. So why is that important? Well, that's important because, for example, if we have two solutions to a homogeneous problem, then the sum of the solutions is again a solution to the homogeneous problem, for instance. But first I need to tell you another theorem here. Moving along here. Actually, this is, well, it's a theorem, but it's also kind of a definition. I guess I'll state the definition first. Definition, given, nth order ODE L of y equal to f, we say y equals to, let's say, phi is solution if L of phi of x is equal to f of x for all x in the domain of definition. For L. What's the domain of definition? I guess I didn't say, but in my original definition, I should say I. I is the domain of definition, all right? It's the set of all independent values of the independent variable for which the differential equation's like making sense. So sometimes you might have like division by 0 or something in some of these coefficients, and so you can't allow that. So it was a theorem which is just this. This is the unique solutions. And so it essentially says this: if we have a sub 0, dot dot dot, a sub n, f, all continuous, on I with a sub n, a sub 0 of x not equal to 0 for all x on I, I'm going to restate this. This is theorem 3.1.2 in my notes. I'm restating it just a little bit here. See, because what this really is the solution to the initial value problem. There's a unique solution to the initial value problem. What's the initial value problem? IVP, initial value problem. Such that, so you're given all of the coefficient functions in the differential equation are continuous, and you're given initial data. And so the initial data is, let's say, y0, y1, dot, 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 y sub n minus 1. These are given constants, okay? That's the setup. You have all that data. Then the conclusion of the initial value theorem, the unique initial value problem theorem, is then there exists a unique, so this notation, right, there exists with an exclamation point, means there exists unique. So since I've said all that, I'll just write it out so there won't be questions about it 3 minutes from now. There exists a unique function phi for which L of phi of x is equal to f of x for all x and I, and phi of x naught is equal to y naught, and phi prime of x naught is equal to y1, dot 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 dot. Phi n minus 1 of x naught is equal to y sub n. In other words, if I have an nth order linear differential equation and I'm given values for the solution, its derivative, its second derivative, all the way out to its n minus 1th derivatives, then there is a unique solution to this problem. Here, x naught is an element of the domain of definition. So the theorem is saying that if you wanted to find a solution that gives you all of those values and all of those derivatives, you can make it happen no matter which point in the domain of definition you choose. You can make this happen. Now, this is not a theorem I'll prove in here, because the proof is advanced calculus and it's somewhat sophisticated. But I will show you a little bit more here. So some examples of this in action. Well, it's not exactly this in action, but just a few brief examples for us. If we were looking at y prime equals to y with y of 0 equals to 1, we can look at this instead as like y prime minus y equals to 0, right? So our L is equal to d minus 1, right? So it's like d minus 1 is my L, and what's my general solution? Y is equal to, excuse me, well, c1e to the x, I suppose. So this one, in terms of my labeling, we have a sub 0 equals to 1, and a sub 1 is equal to minus 1. Those are continuous on the reals, so like the domain of definition for this problem would just be the whole real line, and any solution can be written in this form. All right. If you want me to, so let's see here. If you want to see how the initial value problem, initial unique solution theorem is put into place, I guess you could do this. Y is equal to y1 e to the x minus x1, right? Has x1 comma y1 on solution. So there's how the unique solution theorem works out for that example. See, I can find a unique solution that has the initial data point x1, y1 for any point. How do we derive that solution? So this one here, we'll learn before too long that we can solve that as c1 cosine x plus c2 sine x. All right, so this one here, just to talk about my notation a bit, here we've got a sub 0 equals to 1, a sub 1 is 0, and a sub 2 is 1. And this is the general solution. I'm telling you that we can choose values for c1 and c2 to specify y and its derivative at any point we like. All right?
So a1 equals 0 because there's no y prime term.
Exactly. Another example here, just to try to bring things back down to earth just a bit, but x cubed, now this one's a little bit out there. It's going to be a bit before we get back to how to solve this problem. All right, we'll get to it though, but not soon. So this right here is a second order linear differential equation, and it turns out, and this is not obvious, that y is equal to c1x plus c2 x e to the 1 over x. And to be clear, that I haven't explained why. All right, I have not explained how that is. I'm just telling you it's true. You can check that it's true by actually calculating the derivative and the first derivative of this and the second derivative of that and plugging it back in over here and seeing that it works, right? Going back to what's our definition for solution. Our definition for a solution is it's a function that when you plug it into the differential equation, it satisfies the differential equation. So then again, just to continue my, trying to help you guys understand the notation. So here a sub 0 is x cubed, a sub 2 is x, a sub 1, wait a minute, I'm an idiot. I'll get it eventually here. A sub 1 is x, a sub 2 is minus 1, I guess, for this one. What do you think the domain of definition would be for this differential equation? So here, we better make the domain of definition positive numbers, right? If we make the domain of definition positive numbers, then the leading coefficient, x cubed, is at least not 0, right? And you can kind of see in the solution set that you can't have x equal to 0. But that's a funny interval. So the domain of definition for 1 and 2 and also 4, the domain of definition is just all real numbers. One a little bit different here. We'll look at the nth derivative of y with respect to t just for a second here, equals to 0, right? So this is an nth order differential equation. My L is equal to, d to the n, but now d is d dt. See, so what's the difference? Now I've made t the independent variable. What's the general solution to this? General solution to this is c0 plus c1t plus plus cn minus 1 t to the n, n minus 1, which you can obtain simply by repeated integration. You just integrate n-fold times and you'll derive that solution. All right? So, something I'd like to point out, in the general solution for all of the problems that I've found, there are as many constants in the solution as the order of the problem. So for the first order problem, there's just one constant. For the second order problem, 2 constants, right? For the nth order problem, actually n constants. This is not an accident, all right? So to understand this better, we also need to understand the concept of linear independence. Ooh. So this is a bit much to write out, so I'm going to use the projector here. Because we're about to start looking at determinants of giant things. And if I can find my... Like I said, we're in chapter 3 here. So, linear independence of functions is a little bit tricky because it involves a domain. All right, we have to have a common domain for all the functions in question. But like the definition for linear independence of a set of functions is basically just if you take a linear combination of them and set it equal to 0 as functions, it has to imply that all of the constants, all of the weights forming the linear combination have to be 0. It turns out that this is logically equivalent to saying that you can't write one of the functions as simply a linear combination of the other ones. But how that actually looks like in terms of an equation is just this. So I set C1, C2, Cm times F1, F2 all equal to 0. That has to imply that all of the constants are 0. Now, we get this equation not just for one x, but for all x, right? If that's the case, they're said to be linearly independent. Otherwise, they're said to be linearly dependent on I. And that would mean, like I was just saying in words, you could take one of them, let's say the jth one, and write it as a linear combination of the rest of them. That would be linear dependence. That's what we don't want. Because our solution set, what we're ultimately interested in here is solving the nth order problem. And to do that, we must find a set of n linearly independent solutions to the homogeneous problem. And just to be clear, we're going to try to solve the homogeneous problem to start with. And then we're going to bootstrap our way up to solving the non-homogeneous problem after we do that. All of my examples so far were homogeneous problems. So let us derive a condition to check for linear independence, because like working that out symbolically gives none of you joy. But taking derivatives, I mean taking functions and shoving them in a matrix and then differentiating them and making this specific matrix of functions and then calculating the determinant, that's a joyful thing because it's just a calculation, right? It's not a system of equations. It's just a number you calculate. And if it's non-zero, great, you're done. So to derive that, suppose you have linearly independent functions y1 through ym. Then if that's true, it's true for their derivatives. And it's true for their second derivatives. And it's true for their m-1th derivatives, right? So that means that I can keep differentiating the equation. And if they're linearly independent, the only solution to all of these equations has to be just c1 equals c2 equals dot 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 equals cm equals 0, which we can rewrite as a matrix problem. You see, I can rewrite it as this matrix problem. And so this matrix is a matrix such that this times that vector equals to 0 only has the 0 solution. We learn in linear algebra that that means that the determinant of that matrix must be non-zero. It must be an invertible matrix. And as such, we can demand that this thing, which is called the Wronskian, this is a new Wronskian. You notice the difference? So the Wronskian we looked at for systems, we just put our solutions, ka-chunk, 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 right? But now, for an nth order problem, we actually have to do something. We differentiate to get the rest of the rows. So that's the Wronskian. And what's really cool is that non-zero Wronskian on I implies linear independence on I. That's what this discussion means. If our Wronskian is not equal to 0 for each I, then those are linearly independent functions. Oh, and here, now I'm telling you formulas to a determinant, but we've gone down that road already, right? I usually teach this before the systems material in here. Anyway, so here's some examples. If I want to calculate the Wronskian of e to the ax, e to the bx, I end up with e to the ax, e to the bx on the top row. Then the derivative brings out an a and a b, right? And I calculate, and I get a minus b, e to the a plus bx. When would that be 0?
Well, only if a equals b.
So if a equals b, is e to the ax and e to the bx linearly independent? No, they're the same stupid function, right? So great, it's telling us what we expect, that e to the ax and e to the bx are different functions. They have graphs with different shapes, provided a is not equal to b. How about 1t and t squared? Here we go, differentiate again. Determinant of a diagonal matrix is just the product of, upper triangular is product of the, diagonals, 2. So that shows you that 1t and t squared are, in fact, linearly independent. How about x, sinh, and cosh? Well, here's that one. So differentiate, calculate the determinant. I get minus x, so if x is not equal to 0, I have non-zero Wronskian, right? So now this is where it gets tricky, is 0 Wronskian at one point does not imply linear dependence at that point. Linear dependence and linear independence of functions is a property which has to be understood with respect to an open interval, with respect to a domain. So you have to have the Wronskian is identically equal to 0 on the whole domain to even have hope for linear dependence. And even that's not enough. Even that's not enough, because the Wronskian could be 0, and yet it could be 0 for different reasons on different parts of the domain. It would still be linearly independent. So here's a theorem about the Wronskian. If you have, these are n-1 times differentiable functions. If they're linearly independent, if they're linearly dependent, then the Wronskian's identically 0. However, if there exists one point such that the Wronskian's non-zero, then they're linearly independent. All it takes is 1 point for the Wronskian to be non-zero, and you get linear independence. So it's a little bit subtle. And here's the example which illustrates the subtlety, which is that if you look at the function x squared and x times absolute value of x, these are linearly independent because you can't write one as a multiple of the other on the whole of the real line. So do you guys know what x absolute value of x looks like? So here is x squared, let's say, right? X absolute value of x, it is exactly the same and it's like this down here. So it's actually minus x squared for x less than 0. And this is equal to x squared for x greater than 0. So these are linearly independent functions because one is not simply a multiple of the other for all x. However, these are linearly dependent functions if I just talk about reals, positive reals, or if I just talk about negative reals, right? Then the one is minus the other. That's linear dependent. But if I talk about any domain which includes both positive and negatives, they're not linearly dependent. And yet the Wronskian, when you calculate it, is identically 0 everywhere. So Wronskian being 0 is a little bit, you gotta be careful. Non-zero Wronskian is easy enough to understand. Now here is a theorem that's non-trivial. Y equals 0 is an nth order linear ODE on interval I. And suppose you've got n solutions, y1 through yn. If there's a point such that the Wronskian's non-zero, then that solution set is in fact linearly independent on I. On the other hand, if there exists a point in your domain of definition I such that the Wronskian is equal to 0, then your set is linearly dependent on I. And it follows then that the Wronskian is identically 0 also. So a lot of this comes back to what's called Abel's formula. So I usually work this out by hand. Maybe I'll do this derivation and start a next class. I don't know. But I think I'm going to look at the projector for now. So think about the second order problem. So the second order problem, which I have written up in here, a0 y prime prime plus a1 prime y prime plus a2y equal to 0. Suppose that has solutions y1 and y2, right? So that means what? Oh, man. So I'm saying that a sub 0 y1 prime prime plus a sub 1 y1 prime plus a sub 2 y1 equals to 0, and a sub 0 y2 prime prime plus a sub 1 y2 prime plus a sub 0 y is equal to 0. y2. So in other words, if we plug y1 and y2 into the given second order problem, they both solve the problem. Solve the differential equation. All right. Well, what is the Wronskian in this case? So the Wronskian in this case is what? So the Wronskian of y1, y2 at x is the determinant of, you got y1, you got y2, y1 prime, y2 prime. So the Wronskian is literally y1, y2 prime minus y2, y1 prime. All right, that's why the Wronskian's that. Great. So there's my Wronskian. What can we say about it? Well, it's right there, right? What happens if you differentiate the Wronskian? Well, if you differentiate the Wronskian, you got product rules, right? So two product rules. You get this and that. what did I do here? Did something what canceled out there? Can you guys see it? So the only thing in here that is like test worthy is this derivation I'm going through right now. I mean, like I have put this on tests before, so I'm trying to tell you. Let's see here. So I think what canceled here? Oh, the first derivative terms, right? This and that are the same, but with a minus. So you're just left with the second derivative terms. See that? But then we can use the differential equation like this and that, and we can solve for the second derivative in terms of the first derivative and the constant. So I can trade out y1 prime prime for this, and I can trade out y2 prime prime for that. Then I plug that in to the formula for the derivative of the Wronskian. See this? So I'm literally just putting y1 prime prime here where it was here, and y2 prime prime. I'm sorry, this is y2 prime prime, and then this is y1 prime prime. So that and that. And then you see something else cancels, doesn't it? Can you see, guys, what cancels here? Did you see? I got a minus y1 a2 over a naught y2, and here minus y2 a2 y1 over a naught. So those cancel, and you're just left with the terms with derivatives, and times minus a1 over a naught. So this, but what's this? Well, that's the Wronskian again. Right? That's the Wronskian again. So we've derived that the derivative of the Wronskian is equal to the ratio of a1 and a naught with w. And so can we solve dw dx equals to a1 over w? There's a, I think I lost my minus, didn't I? Typo right here, guys. So sorry about that. Can you solve that by well, yeah, we can solve that. Separate variables, right? Divide by w, multiply by dx, integrate both sides. And there you go. That's the solution. A constant times this exponential. This is known as Abel's formula. And so think about what this means. For a solution set, either this constant is 0 or it's not. If it's non-zero, the Wronskian's non-zero everywhere. But if it's 0, it's 0 everywhere. This is how it has to be for a solution set to a differential equation. Uh-oh. Shush. Go away. Go away. I'm almost done here. What's fascinating, and this I would not try to derive by hand. So like this is actually a fun calculation. We should maybe work through it again next class. What follows is something I would never in my right mind test on because it's like the most technical things in my whole notes, really. And so what I do here is I work out Abel's formula for the nth order problem. And so there's the formula for the determinant of n things. This is a formula, a stone-cold formula for the determinant of an n by n matrix in terms of what's called the antisymmetric symbol. Right? And I work out by some, somewhat complicated calculus stuff that it turns out after much simplification, you still get that the derivative of the Wronskian is minus a1 over a naught w, even when there are n coefficient functions. Abel's formula is still true for the nth order problem, for reasons that, well, they're right there if you want to work through them. But so that's basically it. We'll start up next class here. So that said, let's look at the solution to the test. I don't usually do this, but I feel like I should this time, as there has been some trouble. So now the scores are not visible, so you can just pass them around and take your test, all right? If I happen to see yours on the top, I'll give it to you. Well, let me not call names. Let me not call names. They're in no particular order. So sorry. So while you guys are finding it, let me just go through here problem by problem. So first of all, we have a vector field. We're supposed to find the integral curve. Most of you did set this up correctly. So like dy dx is basically, I said q over p, right? So we got to solve that over that. So we have to separate variables, and a lot of people got that far. And a good number of you did the partial fractions on the x part, which was good. But I saw a lot of, well, that's not entirely true. So sarcastic comment number 1 for today. I'm going to show you guys, check this out. I want to show you a way we can integrate anything. Are you ready? Behold, I have integral of f dx. So what do? I rewrite this as dx over 1 over f, right? You guys with me? Yeah. And then that is the natural log, don't forget the absolute value, 1 over f plus a constant. Done. Check it out. I just integrated all possible functions. Is this true? This is not true, because the only time that you could integrate a reciprocal and get a natural log is when the reciprocal is just x, or x plus a constant. This is absolute nonsense, and it says to me I don't care about calculus 2 whatsoever. This is offensive. Do not do this. Goodness. Oh. All right. Sorry. I'm still in mourning. I'm not sure. Maybe I'm mourning the death of calculus 2. I don't know. So I did see a number of natural log of the denominator here. Like, what on earth, man? Like, you're in differential equations. You're in differential equations. How dare you? Ah. All right. I'll stop. So we can, anyway, the other thing is, like, it was in the homework. This kind of integration was in the homework. It should have been fresh on your memory if you've done the homework. Anyway, so dy over y plus 2 squared is the minus 1 over y plus 2. This also should not have been vexing, but this did stump some of you. All right. Anyway, let's go on.
So is that why you're wearing black?
Yes, there was a murder. Or maybe it's because I'm Batman. I'll explain that later. Let's see here. No, it's probably because there's a murder. All right, so this one here, you know, I can teach you, attempt to teach you techniques, but if you are not careful with algebra, these techniques are meaningless. So, like, algebra's like love in here. You know, if you don't have love, everything's like a meaningless everything, you know, like that, like charity. If you have not algebra, differential equations is not going to work for you. You must learn algebra. You must rekindle caring about algebra. I know you're like, I didn't have time. Yeah. All right, so anyway, so x to the fourth is what we get here. And so multiply by x to the fourth, reverse product rule. Again, if you're thinking through this, you should have realized if you didn't get x to the fourth here, this does not work. Some of you just wrote that down because you're not really thinking through the process. If you're thinking through the process, you should be able to figure out x to the fourth was the integrating factor. Yep.
Where would you suggest we go in order to reduce that algebra?
First of all, the homework. Second of all, I don't know. But like, how do you view algebra?
There's a lot of algebra that shows up on the exams and stuff that isn't specifically on the homework. So there's only so much homework to go to.
This algebra was on the homework.
I know, I'm not saying there wasn't a decent bit of it, but there's more algebra we need practice for future exams.
Do you recommend admissions?
I mean,
Those as well.
right, I'm going to continue. I think the algebra is in the homework already, but so here, I mean, we can always do more homework, I suppose, but okay. So reverse product rule, integrate both sides. We get, of course, so over here, this is a u substitution, right? U equals x to the fifth. So this is nothing more than 1/5 sine x plus a constant. And a number of you did get this one right. So yay, that was good. Most of you did know the integral of inverse sine. That was wonderful. You picked up on that. That's good. That's very good. I mean, that's really calculus 2, but that part stuck, but good. And then here, a number of you got stuck on this one. But this is a u substitution. Like, you just make u equal 1 plus y cubed, and then this is the du, basically. So I wasn't thinking that would be a stumbling block for a lot of people, but it was. So anyway, so we get this plus that plus that. Again, you only need one of these. Some of you are still putting 2 copies of that into your solution. That means that you're really not done studying. That's my best explanation for that. This one here was, again, a homework problem, but the format's slightly different. I actually told you v equals y over x, you know, so y is equal to vx or xv. As I was telling you guys, when we have a substitution, we have to differentiate the substitution rule to learn how the derivative of the substituted variable relates to the derivative of the original variable. And when we do that, we get this, which is actually easier than the homework. It's in fact inverse tangent of the log of x plus a constant. There you go. Some of you are not adding constants when you integrate. You know, you're going to lose. I mean, you got to add constants when you integrate at some point. All right, so the next one here, problem 5. We're supposed to find the orthogonal trajectories. So I flip it and put a minus, integrate both sides, 1/2 y squared minus x plus cosine. Solve for y, I get that. I really should have asked you to find the explicit solution, but I failed in that. So I had to either allow this or that as legit solutions. Either one would work, but yeah. Problem 6. Again, as I said in the announcement, I'm sorry if the not knowing the eigenvalues tripped you up here. I really would have told you if you guys had asked me. I didn't mean to, you know, stump you on that. I'm sorry about that. But in any event, this is what I was talking about in the review session when I said, like, you know, the determinant of a block diagonal matrix is the product of the blocks. So now, in terms of this, for you guys, basically when you did the expansion, you should have noticed that you've got a 42 minus lambda on 2 terms, which means you shouldn't multiply it out. Like, you don't just mechanically multiply stuff out. When you're factoring, if you have a common factor on 2 terms, you pull it out. You don't multiply through. Like, that's just, you know, factoring. Anyway, so 42 and 1 plus or minus 6i was what the story was here, which ends up giving me 0, 0, 1 for this one and whatever it is down here for that one. And again, so I am sorry if not telling you the eigenvalues was what stumped you here, but I don't, well, anyway. So there's that. So generically speaking, though, some of you were trying to, like, you know, get some points, but you knew you weren't quite there. But you still put down a solution which you didn't have constants in it, right? There's always a C1, a C2, and a C3, and a third order, order 3 problem, unless you have initial conditions, right? So then problem 7, again, was like a homework problem. So this is just the 2x2 problem. You must be more careful with your algebra. Many of you did not get lambda equals to 1 twice. You got lambda equals 1, lambda equals 3, or I mean, I've got a bunch of different things other than 1 here, and that means that you need to work much more carefully on the algebra. That's all I can say, I guess. I mean, there's some other things you might learn in terms of, that's just it. But all right, so eigenvalue 1 it gives me that vector, and then I have to solve the chain condition as we talked about, which I choose this, but there are other choices. Then the magic formula gives me this interesting solution over here, as well as that eigensolution, and that's it. And then problem 8 was supposed to be a gift, but it was not freely taken. And so, like, this is, again, was very much related to, like, problem 23 in the homework. So this is the eigensolution, the generalized eigensolution, because u1 is a generalized eigenvector of order 2. And then this is these are the complex solutions. So a lot of you didn't do that one. So if you know how to do that one, it doesn't take more than about 2 minutes, that past one. This is a bonus question, so if you didn't get this, it's okay. This was a genuinely new problem. This was honestly new problem that I had not shown you before, but I think there's a chance that you could have gotten this if you thought about it a little bit in the right way. So I think the easiest way to do it was to remember that we proved the derivative of the x matrix exponential was a times the matrix exponential, and then if you just plug t equal to 0 in, that gives you a. And then, but a lot of you, there were like 5 of you who got this, I think, which is great. That's really good. That's really good. And then problem 10 was, there's not much to it really. You just calculate the exterior derivative, and since the exterior derivative is non-zero, but we proved in the homework that d squared was 0, so you can't have both. You know, if d squared is 0, but d alpha is non-zero, that's, you know, that's not possible. So that was it. That's the test. And so the high score on the test was 151. And there are other scores, you know, in the 130 to 120 range. Could be done. It's possible. Not important. Lower. Much, much lower. That said, I will drop the this test and replace it with the final exam score if that's helpful. It will almost certainly be helpful for most of you. And also, as a show of mercy, I am also providing a bonus project to do since I have a grader. The other thing I'm going to do, which is a merciful thing to you, is I'm eliminating teams. You will all do your own mission 2. So that should fix things a bit. Since I have a grader now, I don't have time to grade this many homeworks, right? So I have to do teams. But since I have a grader, and I think it would be helpful to you to do all the homework, everyone will do team mission 2 on your lonesome. All right? So I guess that makes the team simple enough. You're all a team of 1. Is that like an Army advertisement now, or in this Army of 1, or what was it? I'm sorry, I'm remembering commercial advertisement campaigns from like the 1990s or 2010s or whatever.